And now, a little case study actually that I had been able to do when I was consulting with rigidized metals that uses computational design. So they have a small outbuilding that they wanted to kind of repurpose into office space or additional meeting space. And my proposal to them was to put, they had, was an existing, what they call a freight house, an unloading house. So these large expanses of openings on them that I suggested that we glaze with opening doors. And their concern was because this is an industrial setting, there's no people around at night, that kids would just throw rocks through the windows. And so my solution to that, or my suggested solution to that, was to put a screen up over it. And the reason, the first go-to would be to put a mesh kind of or a barrier system over it. And the reason, the design reason for not doing that was that it would look like the place intended. It felt unsecure. That the idea that we had to put bars over the windows or protection over them because it was anticipated that they were going to be damaged. And so, by creating this kind of pattern system that still had this kind of functionality to it, it was no longer sending that kind of a message that this was there for security. It looked like it was more there for decoration and embellishment to the surfaces of the window systems. And so there were some design briefs that went along with this to determine the kind of layout of the pattern system. And this is based on that idea of computational design. And we've seen in the Watson screening project the idea of the Voronoi development of a surface, which is a patterned surface. In this case, the Voronoi, as we used it, we defined that we wanted to have a certain number of openings with none of the openings being over a certain diameter. And so by programming that offset, that diameter, we could limit the idea of the size of an object that might be thrown at the window in order to break the glass. So it was anticipated that if you had a large enough rock to break the glass, the odds are if it was under a certain diameter of opening, the rock would be deflected away and it would be very difficult to break the glass. And so with that, this is a construction document of what that final panel set is. So you can see there's the little flanges that return in order to make it a panel system. And it's kind of a close-up of what the final pattern was developed for it. And you'll notice that there's a variation, and it's really actually more difficult to see in the final product than it is in this graphic, which kind of should be an indication of the need to maybe overemphasize patterning in these kind of systems. But part of the thinking behind it was this was the idea of kind of waves of a field of grain. This is in a historic district or a historic area, industrial area of Western New York's waterfront, where we have these large grain mills. The company Rigidized Metals is also the owner of some of these grain mills. And so this was the idea of wheat and maybe blowing in the breeze kind of effect. That was just the underlying theme that I used to kind of develop this idea of the patterning. And so it's a little hard to see in this image, but you'll see some areas where there are little appear to be like dots. Those are additional seeds that I added to the pattern system in order to create greater density. So where there were more seeds, there were actually where there were more seeds, there were less density of the pattern. And so actually here's a great, this shows you that idea of that placement of seeds that was used. Those are hand placed points. So I just went along with a mouse and dotted some extra points in, and then that was immediately input into the Voronoi functional system and created this kind of variation in the surface pattern. So the software that this is done in is in Rhino and using Grasshopper, but the techniques are directly transferable to being used in Dynamo and Revit programming environment. But at the time, I had no access. Actually, I didn't even know how to use Revit at that time. So I was using this environment. And so it's really actually quite simple. If you look at this, this is a description of all of the programming elements that were needed to create that panel system. So the idea is I have sliders that create the position of the panel within the realm of its construction. I have something that determines the overall size of the panel. and then I offset it by a certain amount. In this case, it looks like it's 1.57 inches if you look up right above my head there. So I could control how large those openings were or how small they were. And then I just offset those in order to create that kind of a thickness that gave me a digital layout that we could then pass over to the fabrication shop that could code that as a program for the laser to cut out. And so here's an example of that, or here's the kind of finished product of those screening systems. So the center screens are actually retractable. They slide back and allow you to open up the doors and move in and out over onto the deck system of this building. If we're meeting live, it's the sign in. And then I kind of want to conclude with some other things that I've been doing experimentally with computational design. So we'll do a little bit of this experimentation. The idea here is I've mapped a graphic, a visual graphic of whatever it is. It could be trees, a mountain, water, in order to create, and it took the density of those pixels and created a depth map that I mapped to a continuous surface. And then using computational design, I divided that surface up and created those returns that go back in order to make 3D printable elements of that surface. And this is all based on obviously techniques that are available really only through computational design. You could imagine how tedious it would be to have to come up with creating all of these panels in order to create this kind of a textured surface. And so this is all done so that it could actually be driven directly to a 3D printer. So in the future, if we were to, if surfaces or whatever it was wanted to be panelized like this and directed to a 3D printer that was, instead of printing plastic, was printing concrete, we have a way, there are easy techniques where we could create these kind of panelized construction systems. And to give you an idea for the intensity of the code work that is behind that, so here we have on the left, I kind of zoomed into it. We have the idea of importing that image. You can see the image on the top. It's a it's a mountain range with a reflection over it. A small image that's imported in. We scale it to fit the panel array that we want to have. We make a panel array. And then over my head, that's all of the computational elements that are designed to make that panel thick, bring the return edges in the returns in order to make it a three-dimensional object that could be printed by a 3D printing machine and then erected onto a building. And so while that code looks like it's really intensive, it's just a repeating of elements like make a side panel, make another side panel, make a return panel, make another return panel, and on with that. So once again, just to really, for me, going through this experiment was really eye-opening about the power that this technique has. Just a few miscellaneous things that I want to touch on before we quit. One is, or before we end this section, one is the idea that in the computational design world, we really move quickly away from this idea of planar flat surfaces because of the complexities of the things that we want to analyze and work with. And we move into what is called a UV space. And this is really just kind of a nice visualization of that. This is also covered, I think these are extracted from the Dynamo primer. But instead of X and Y, we have U and V space to define a point on a surface. And then instead of that Z, we have what's called a normal vector, which means that at any given curvature of the surface, at exact point, if we were to draw a plane across that point, it would have a vector coming out directly perpendicular, obviously, to that surface plane. And that would be called the normal vector. So we have UV space, and then we have the idea of constructing these perpendicular planes. And that gives us a whole new kind of a geometry with which to kind of empower us to be able to calculate on these really very complicated surfaces that we want to create. The other way of looking at it is by understanding these complicated surfaces that we may randomly create by doing just manipulating forms as generic models with spline lines. Once we have that, we have a methodology, a mathematical way of analyzing any place on that in order to create a panel or an attachment point or to create a void space, anything that we want to do to manipulate that surface, to thicken that surface, we can define it in UV space and at each individual point with that kind of a normal planar vector space. And this is just examples of that kind of being able to take a curved surface and then find points on it in order to define panels, panelize it, and then create actually planar surfaces from those that could be physical panels. So that's just the geometry end of it, but on the computational empowerment, this is something that Autodesk has been doing. This is using computational design, and we'll get into this idea of generative design in order to do office layout. So in this case, the orange is representing a path through the space. Um, the things that are changing are the wall partitions, the construction of work surfaces, and other shared common areas within that space. And then the idea is to input different parameters in order to optimize that, all with the idea that we have objectives of what we want to do, like adjacencies, best views, most people having the most optimized kind of seating for the best views. And so that's really one of the reasons why you may have an interest, besides just creating geometry, is the ability to analyze complex data in building systems. And where we're going with that, on the computational side, and this is actually going to be the side that we don't see our data necessarily, but this is how we are able to start doing things like making flexible, and I'll let that run again. Here we have a parametric model that changes its arrangement according to the amount of square footage that's available. So it goes from a 1-bedroom to a 2-bedroom, or a no bedroom to a 2-bedroom apartment, all based on this idea of a volume or envelope that can be contained within it. And so that'll wrap up this part of our actual introduction to computational programming.